So here I am, a baby picture of me. This was back in 1990 when I was the director of the National Center for Supercomputing Applications, and this is the Cray YMP. It was $15 million. It could do gigaflops, billions of floating point operations per second. And the NSF net backbone, which became later the internet, was megabits. Well, now you go forward 15 years, that same computing power is in a $1,000 or less, by now less, laptop, same computing power, exactly. In fact, your PC probably has more memory than the YMP had. And a megabit to the home is completely normal, right? So this testing things out at the elite frontier of scientific research, and yet them ending up over a decade or so as a mass market, happens over and over and over again, which is one reason that we actually fund science in this country. For instance, the NSF is funding the first sustained NSF supercomputer called the Blue Waters at the University of Illinois. It'll be 1 million times faster than that YMP. And it's partly because of parallelism. Just like the brain has a very different form of parallelism, but that's why it's as powerful as it is. And what this lets you do is what computers are much better than humans are at, is to take the partial differential equations that define the laws of physics and solve them in high resolution of space and time. And so you can see back in '87 when we first took the equations governing the atmosphere with the solar radiation coming in and the equation of state of water going between water vapor and ice and so forth, you could get something that looked like a self-excited thunderstorm. Now, with the much faster supercomputers, you're actually able to zoom down in and to see phenomena like vortical cores forming that actually are tornadoes within a very, very large thunderstorm, all of which are being simulated. So if you look at the NSF supercomputer centers where they have teraflops, so 10 to the 12 floating point operations per second, they're being used for all kinds of things from better fuel cells to bird flu drugs, Alzheimer's, and so forth. So vast a range of scientific applications. Now here I just scanned this out of Ray's book yesterday, and this is going back through this period from 1990 on up of the various computers that are in places like the Department of Energy labs and so forth. The two red dots I added are petaflop, that's 10 to the 12, 20 to the 15 floating point operations a second, and exaflop, which is 1,000 times that, just like a petaflop is 1,000 times a teraflop. And so you can see that in this period from 2010, where already we have sustained petaflop, until about 220, this next decade is where we're going through the 10 to the 16th, which is right there, which Ray considers a conservative number, I love that, for the computing power of a human brain. Now I'm not going to go into all the ways you can figure out what is a likely number for the computing property of the brain, because he covers that in his book and he has many references. But I just want you to see that you're going to be living through that period.